So now that we've talked about monitor objects and condition objects and reentrant locks and so on and so forth, and we've talked about semaphores, what we're going to do is talk about how to implement a fair semaphore using something called the specific notification pattern, which I've alluded to earlier, but now we'll go into much more detail to discuss. And we'll use this pattern. This pattern can be used for a variety of things. We're going to use it to implement a fair semaphore. And the reason why you should care about this is because the next programming assignment is going to have you do this. So let's first talk about what a fair semaphore is. So a fair semaphore is basically one that allows waiting threads that are calling acquire to obtain their permit or permits in so-called FIFO order, first in, first out order, which is just a classic queue. So whoever's front in line is the next one to go. And what this does, when you think about how the semaphore works, is it has these things called internal points of execution within the semaphore methods, basically the things that do the queuing. And it's going to be set up so that whoever's been waiting the longest is the one that gets the chance to run next. And so this is a subtle point. It's not the order in which acquire is called. It's the order in which they reach the ordering point. And the ordering point is, again, the thing that they use to determine the order in which things are going to be put to sleep and the order in which they're going to wake up. And to make this tractable and to get a sense of how patterns can make a difference in real application programs, especially concurrent programs, we're going to use the specific notification pattern to guide the implementation of the fair semaphore. So that, of course, raises the question, what is the specific notification pattern? So I'll kind of summarize it for you. The place to go look for more information about it is this article, which is about 20 years old, but I have a version of it which you can download here from my website. And you should read it because it talks about the problem in general, and then it gives an example. And the one you want to focus on is the example in listing 3, which doesn't do exactly the same thing as you're doing, but it gives you a good sense of what to do. So here's the context. You have a family or a set of threads in Java that want to cooperate in order to synchronize their use of shared resources in a fair way. So we've already got the context for this, of course, which is our Palantir manager application. And we've got a bunch of threads. And the way we want to make it work is we want to make sure that they take turns getting access to the Palantir. We don't want one thread / being to greedily come along and keep gazing and gazing and gazing, and all the other beings starve. That's what we're trying to avoid. That's why we want to be fair. So the problem here is that Java built-in monitor objects, as we've discussed, don't give you any built-in way to control the order in which threads acquire access to a shared resource. And that's because they support this thing called haphazard notification. So if you have a bunch of threads that are waiting to get access, that's sort of what we show here. We have a bunch of threads that are waiting, and let's say they're in order of 1, 2, 3, 4. Haphazard notification might say, well, we're just going to take the guy at the end and let the guy at the end go next, which isn't fair, right? Because the other ones have been waiting there longer. And the particular issue here is after notify or notify all is called, the operating system and the virtual machine dictate the order in which a thread or threads get awakened, and you have no built-in control over that. So it just sort of picks one. I won't say at random because there's a method to the madness, but it's perhaps not FIFO, which is maybe what you want to have, because that way you can ensure fairness. And so that part of it is selecting a thread and then scheduling the thread to run after this. So part of it's selecting the thread and it's scheduling of the thread or threads to run after notify or notify all gets called. So those are the two things that are not under your control with the built-in monitor object. So what are we going to do to solve this? Of course, we're going to apply a pattern. What's the pattern? It's the specific notification pattern, originally described by Tom Cargill. And what this does is it allows you, the programmer of the abstraction that uses the pattern, to perform a non-haphazard means of selecting and scheduling threads to run. So you can control, the implementer of the abstraction, can control the ordering. And the paper goes into a bunch of examples. We're going to look at a very particular one. in particular, you can designate exactly which thread in this family of threads should proceed after notify or notify all gets called. You control how that's going to work. So here's a quick outline of the solution, then we're going to step through it in much more gory detail so you can understand how it all works. So the basic idea here is that you're going to essentially put threads to sleep by making wait calls on monitor objects. But what we're going to do that's different from a built-in monitor object is we're going to end up having essentially one monitor object for every thread. So we're going to have an internal linked list, or queue, but we can use it as a linked list. And we're going to go ahead and queue things up. And in the queue will be monitor objects, which is kind of funky, right? So we're going to have nested monitor objects. We have to be very, very, very careful how we program these things to avoid the nested monitor object lockout problem that we talked about before. So there'll be one monitor object for every thread. Each thread has its own monitor object that it's individually going to wait on. And the thread that's been waiting on its monitor object in the linked list of monitor objects is going to be notified, and the threads will be notified in FIFO order. So whoever's been waiting in this linked list the longest is always the one that's going to get a chance to run next when something is free. So that's the high-level view of this. All right, so now what we're going to do is we're going to use this pattern, which I've outlined here, in order to implement a fair semaphore. We could use it for all kinds of other stuff too, but we're going to use it to implement a fair semaphore. And I'm going to give you a detailed visual analysis of how this algorithm works, this pattern works. And then your job for assignment number 4 is going to be to translate the visual description plus the skeletons that we'll go through in a little bit and implement the fair semaphore using the specific notification pattern. Now, this turns out to be very subtle. It's not a whole lot of lines of code. The lines of code are fairly limited. It's one class. It's called fair semaphore, and grad students have one variant. Undergrads do a different one. But it's not the number of lines of code that matters. It's the subtlety of how to implement the pattern that matters. That's the part that's fairly tricky. So I'm going to walk through it and explain it to you verbally with pointers to visual depictions of what's going on. So let's assume, for sake of argument, we've got ourselves a fair semaphore. And the example I'm going to talk about here is going to be one that uses the monitor object as the basis for the implementation. As you'll see, the actual assignment 4 has 2 different versions, one that uses monitor objects, which the undergrads will do, and one that uses reentrant lock and condition object, which the grad students will do. They're roughly the same. Quite frankly, there's certain little cool optimizations you can do with reentrant lock and condition object that we'll talk about when we talk about the skeletons, but they're roughly about the same amount of code in order to implement. So what we're going to do here is we're going to have a fair semaphore, and we're going to make a new fair semaphore instance with a single permit to begin with. So we're sharing one resource between multiple threads, thread T1 and T2, and there could be other threads as well. And then thread T1 is going to come along and call acquire. Now, of course, it should be able to acquire it because it's got a count of 1, and we'll talk about that. So what will happen here is that thread T1 is going to acquire the semaphore immediately since there are no waiters. That's the definition of a semaphore. And that's kind of the fast path, the happy path through the code. What will happen, of course, in the implementation of this, if you think about the acquire method, and you'll have to do things much like we did before, where you'll have acquire and acquire interruptibly, I think, two different forms of acquire, which you've already dealt with in your earlier implementations of the semaphore. And so what this is going to have to do is it's going to have to synchronize access to the intrinsic monitor lock, the one on fair semaphore itself, in order to protect the object state from race conditions. And what is the object state, you may ask? It's going to be things like the permit count and the linked list that's used underneath the hood to keep track of things that are waiting. So there's just some shared state that's part of the fair semaphore implementation that has to be protected. Now, remember I mentioned they have this linked list. I'm going to call it Q for the purposes of our discussion, but the implementation of it will actually be a linked list. So if the queue is empty, meaning nobody's waiting, and the permit count is greater than 0, which it is to start out with, that's the fast path, that's the happy path. All you have to do is decrement the count. So it went from 1 to 0, and you return, and when you return, that releases the intrinsic monitor lock, and that thread exits the critical section. Okay, so far so good. That's really easy code. Nothing the least bit tricky there at all. All right, now let's say, for sake of argument, that thread has got the semaphore acquired, and now thread 2 comes here, and it tries to acquire the lock, or it tries to acquire the semaphore as well. Now things are going to get a lot more interesting because the count's 0, so we have to queue this thing up somehow. So what's going to happen here is we're going to have to create a new wait object, which I'm going to call wait obj. And every thread that comes along to get the semaphore when the semaphore count is 0 is going to have a wait obj created for it, which will be put into the queue so that we can queue up the waiting threads in FIFO order that we can control. We're going to be able to control it because we're writing the implementation for that. So we make this new wait object that can be synchronized upon. That's important. We'll talk about that later. And we queue it up in the wait queue. Now, the thing to remember about this is really subtle. And when you read the Tom Cargill paper about specific notification pattern and look at the code examples, you'll see what he does. But the key thing to remember is that the queuing of the stuff that we're doing here and the waiting needs to happen outside of the fair semaphore's critical section. And this is to avoid this nested monitor lockout problem that I talked about before. So this is subtle code. It's not hard code. It's not like you're writing 100 lines of code. It's like 3 lines of code. But man, oh man, you've got to figure out where to put those 3 lines of code. If you do not get that right, your program is going to deadlock and weird things will happen. Okay, so then what's going to happen, again, outside of the critical section of the fair semaphore, the thread that's trying to acquire a semaphore permit is going to synchronize on wait obj. So remember, we created this wait object, and now we're going to have to go and synchronize on it because we want to make sure that the wait object is not prematurely deleted in the release method. We'll talk about release shortly. Release is what's going to give back a permit. So that, of course, will then synchronize on the monitor lock, and that will update the wait queue safely. Now remember, the wait queue, which is this linked list, is part of the fair semaphore state. So that has to be protected by a lock. We cannot be accessing we can't be updating the queue without that lock held. So this is where the subtlety comes in. So what you're going to do then is you're going to add the wait object to the end of the wait queue. In other words, it's going to be stuck at you're going to add it using, since it's a linked list, you'll use add. Add sticks it at the end of the linked list. So now the wait queue is going to have a new entry in it. Permit count still 0, lock is held, wait queue has the item, and then we're going to go ahead and release the lock and leave the fair semaphore monitor object's critical section. Now here's the really crucial thing. The wait that's called on the wait obj must be done with wait obj synchronized, but without holding the intrinsic monitor lock of the fair semaphore in order to avoid self-deadlock. This is really, really subtle code. Again, I recommend you go read the Cargill article. He gives you some pointers on how to do this. This is tricky. Again, it's not hard. I mean, it's not long code. It's just really tricky code. And what will happen here is that when you call wait, that will atomically release the wait obj monitor lock as opposed to the fair semaphore monitor lock, which is a different monitor lock, and it'll go to sleep waiting for someone to notify it. There'll only ever be one thread that notifies this. This is actually a really interesting and very rare situation where you'll actually call wait on a monitor object without putting it in a loop. You almost always call wait in a loop. In this particular case, you do not call wait in a loop. There's a reason for that, which we'll see when we talk more about it. OK. Now, if an interrupted exception is thrown during a blocking call to wait on a wait object, then you have to have an exception handler, and you have to reacquire the monitor lock. And this is the monitor lock of the fair semaphore in order to be able to access the wait queue safely. So the thing to remember, always remember, the really, really, really important, go back and listen to this video multiple times if you're wrestling with this. Whenever you access the shared state of the fair semaphore object, which includes the permit and the wait queue, you have to make sure the intrinsic monitor lock for the fair semaphore object is held. And the way you would do that with a monitor object is by using synchronized. If you're doing the grad student version, as we'll see, you'd end up just doing a lock on the reentrant lock that's for that fair semaphore. So make sure that you always hold that intrinsic monitor lock for the fair semaphore whenever you're accessing anything that's shared mutable state. This is really going to give you a deep understanding of shared mutable state, much deeper than the discussions we had before. So you're going to have to do that, and then you're going to try to remove the wait object from the wait queue, but it may not be on the queue. And so that means you're going to have to do it in a non-blocking way, because it may have been taken off by the release method. We'll talk more about that later. So you've got to be very careful. If you can get it off, that's great. If you can't, don't block, because you'll be in big trouble. And then after you do that, you rethrow the interrupted exception. So the point here with exception handling is often the case with exception handling. You may have to clean things up if you may have to use the exception handler to clean up resources, and this is what this is all about. OK, so that's handling the case where you've got thread T1 and T2. Thread 1 has acquired the lock, and thread T2 has come along in order to try to acquire it acquired the semaphore. Thread T2 comes along trying to acquire the semaphore. The semaphore permit count is 0, so it has to go ahead and be put onto the wait queue. So now we've got thread T3 comes along, and it's also going to try to acquire the lock. Now this is actually very much the same code. I just want to show you what happens and how the wait queue can grow over time. So we come along, thread T3, it calls acquire. Of course, the permit count is 0. And so what we do here is we create yet another wait object, which is separate from the one that was used for the first waiting thread, which was thread T2 in our scenario. So we create a new wait object. And you'll see that this is wait object is an instance of a class called waiter. And the waiter is just simply implemented differently for the grad and the ugrad version. And then you'll end up synchronizing on the wait object to make sure it's not deleted prematurely in release. And then you have to go ahead and synchronize on the monitor lock, which is the intrinsic monitor lock for the fair semaphore, in order to update the wait queue safely, because we're going to stick this wait object here into the end of this wait queue here. So now you can see a little transition here. Right? So we go from one object in the wait queue. Now we have 2 objects in the wait queue. And it's added, of course, so it'll go at the end. So it'll be stored in FIFO order. So remember, the whole point of the specific notification pattern is to control the order in which things are performed. We're sticking stuff at the end because we're doing a fair semaphore, and we want to make sure it occurs in FIFO order. We then release the fair semaphores monitor object intrinsic monitor lock, and we exit the critical section. And now we'll be waiting on wait object B, which is this guy here, which is different from wait object A. And once again, we have to make sure that we do this without holding the fair semaphore's intrinsic monitor lock to avoid self-deadlock. Really, really, really important. Do not get self-deadlock. I guarantee you, if you do not do this correctly, you will run your program, you will run the tests, and stuff will freeze, and you get a weird exception that says, you know, your test timed out after 2,000 milliseconds or whatever the number is, and you will post a message to the discussion board saying, why is my test failing with this weird error? And the reason is you've got self-deadlock. The reason is most likely because you have self-deadlock. And then wait, you'll call wait, the thread that wants to go to sleep, awaiting its chance to get access to the semaphore, will call wait on wait object B's monitor lock, and it'll block until it is specifically notified later in release. Okay, so that then covered the scenario. We've got, then we got 3 threads. Thread T1 has got the semaphore. It's off doing its thing. Threads T2 and T3 are blocked in that order using the wait queue to queue up the threads that are waiting on the wait objects. Each thread waiting on a different wait object, each wait object put into a wait queue in FIFO order. So far, so good. Any questions about what we're doing so far? Okay, the last piece of the puzzle here is what happens when someone comes along to call release. This could be thread T1, this could be thread T4. It doesn't really matter. It's just some other thread. Definitely not threads T1 and T2, or sorry, T2 and T3, because threads T2 and T3 are blocked here on the wait queue, waiting their chance to run. Whoops, this should probably be T4, not T1, but it could be T1. So it's just the 4th thread. And so what thread T4 is going to do is it's going to call release. And the intent of release is to make sure it releases the longest waiting thread. In other words, in this case, thread T2, which is waiting on wait object A, which is at the head of the queue. Okay, so how is this going to work? Well, as always, whenever we come into this thing, and anytime we want to access shared state, like check the permit count, check the wait queue status, et cetera, we have to first go ahead and grab the intrinsic monitor lock for fair semaphore. And we need that because these guys are shared mutable state. We don't want them to be corrupted. All the usual reasons to use synchronization. Okay. So there's a cool little optimization we can do here. And if the next wait object, in other words, wait object A, because that's the one that we're releasing, if that one is in the wait queue, that means another thread is waiting to access the semaphore. So in this case, we're going to do sort of a short circuit, and we're not going to increment the permit count. We're simply going to wake up the waiting thread, and it'll just keep going, because we don't want to have to wake up, we don't have to increment the count and then have that guy decrement the count. We're just waking him up. So we're kind of saying it's even Steven. I'm releasing somebody and waking somebody up, and therefore there's no need to change the permit count at all. The only reason you would increment the permit count if there wasn't anybody waiting, because then there could be somebody waiting in the future. But since we're waking somebody up, we don't have to do anything to the permit count at all. So what we're going to do here is we're going to acquire the monitor lock on this wait object. This is the one we took out of the linked list. And then we're going to inform the thread, in this case, this is thread T2, that's blocked on that wait object that it now can run. And how do you think we're going to inform it? Notify, exactly. And that's the key thing. Notify, not notify all. I mean, you could call notify all, but there's only ever one thread waiting on it, so it would just be a wasted confusion. So you want to call notify. So you're going to notify that next object, which is the one that's going to be used to let that thread, in this case T2, wake up and do its thing with the permit acquired. And then you go ahead and unlock this monitor object, so that will allow the thread that's waiting, in this case T2, to continue. And then you release the monitor object for the critical section for the fair semaphore. The other case in release is there are no waiting threads. So if there are no waiting threads, in other words, this is not the case here because we've got a queue of threads, but if there were no waiting threads, then, and only then, do you actually increment the count by 1. And that way, some other thread, that way you've updated the state of the semaphore such that when another thread comes along later and wants to acquire it, it's got a count that's incremented by 1, so that helps the next thread in its determination of whether it can grab the semaphore and continue. Okay, so that's the end of the discussion of the specific notification pattern.